Yeah, anytime is fine. Thank you.
Yeah, cool. All right. Okay, ladies and gentlemen, welcome to this keynote speech session. My name is Ching Tang from Peking University. And I'll be your moderator today. So today, with my greatest honor, we have Dr. Max Wei sharing with us. Dr. Wei, thank you very much for the talk. Maybe just a little bit of hospitality first. So today's talk will be divided into two parts, which Dr. Wei will deliver the talk for about 40 minutes first, and then we leave 20 minutes at the end for Q&A session, okay? For the audience, you are more than welcome to raise questions in the Q&A session, or if you prefer, you could also key in your questions in the chat box. All right. Before I hand over to Dr. Wei, let me briefly introduce our keynote speaker to the audience. Dr. Wei is a research scientist at Lawrence Berkeley National Lab. He has extensive experience modeling decarbonization pathway for California and techno-economic studies of building electrification, zero net energy homes, and emerging technologies. He's really experienced, and he has 5 years of experience in energy analysis and 10 years of industry experience in advancing manufacturing and technology development. So his talk today is entitled Advancing Climate Equity and Heat Resilience in Disadvantaged Urban Communities. Okay, so without further ado, Dr. Wei, the stage is yours.
Thank you very much for the opportunity to present today to the Applied Energy Symposium on low carbon cities and urban energy systems. Can you see my screen and hear me?
Yeah, it's clear and loud.
Okay, thank you. So it's my pleasure to discuss the topic of advancing climate equity and heat resilience in disadvantaged communities, and to share some of our recent results and recommendations on from recent work in California's Central Valley. So I'll start my talk with some definitions and some landscape, and then I'll give an example of some equity and resilience work in California, Cal Thrives, which is on heat resilience. And then I'll discuss some next steps and future work in policy and RD&D, and then to the Q&A. So I do think that definitions are important here because some of these terms are not really universally well-defined. And then I'd also just like to share my own view on how this fits into the overall landscape of decarbonization. So first, just a few comments on what are disadvantaged communities. So disadvantaged communities refer to areas that are that suffer from a combination of economic, health, and environmental burdens. So in other words, they're both low income and they have high pollution burdens, high unemployment, higher crime, and poor underlying health in the community among residents. And in particular, in California, there are multiple challenges in the Central Valley of the state. Much of the Central Valley of California, which is a flat agricultural region, is highly disadvantaged and underserved. And this is a map of disadvantaged communities using the Cal Enviro Screen tool, just showing that the redder areas are more disadvantaged and that residents suffer from the worst air quality in the state and have the highest utility bills in the state. So next, I'd just like to address what is equity, and equity of what, and equity for whom, and equity where. So energy or climate equity is about the just or fair distribution of benefits and burdens. And here it refers to benefits such as clean energy access, clean technologies access, so things like solar PV or electric vehicles, And the burdens refer to air pollution and water pollution. So it's really about the fair distribution of these benefits and burdens. And for whom it usually refers to residents and neighborhoods and sometimes to businesses. And the focus really is on areas that are typically low income and suffer from high pollution. So really, there are a lot of these mapping tools in the US for California, but also for the overall country. And here's just a cartoon talking about inequality, equality, and equity, where the benefit here could be fruit from this tree, or it could be access to solar PV or access to electric vehicles. And that's not really necessarily equally distributed. So the latter in this case can refer to financial assistance or incentives to residents to be able to better access the benefit, here fruit, or it could be access to clean energy technologies. But if the financial assistance is equalized, then there's still some groups or some people who cannot access the benefits. So you may need more financial incentives or higher rebates in this case in disadvantaged communities for residents there, which speaks to achieving greater equity. And of course, there are indicators for international wealth inequality. This is not a direct measure for climate equity, of course, but just international wealth. But it's sort of like a proxy, and you can see that there are countries with higher wealth inequality in all the continents in North America, the US, unfortunately, South America, Asia, Africa, maybe not so much Australia. And that also income inequality is rising. So rising inequality is affecting more than 2/3 of the globe, but it's not inevitable per a new UN report from 2020. Okay, so what is resilience? And here I'd like to discuss and describe resilience of what, resilience to what, and resilience to ensure what. And again, this is not a universal definition, so it varies from reference to reference and from source to source. But I think it's important just to highlight what's being referred to in one's work or study. So this definition, I think from the Department of Defense actually, states that resilience is the ability to anticipate, prepare for, and adapt to changing conditions, and to withstand, respond to, and recover rapidly from disruptions. So sometimes resilience is mainly in the latter sense of recovery from emergency disruptions. But in this framing, it's really merging two concepts, adaptation and resilience. So for sure, in the parlance or in the usage today, there's kind of an overlap between these two concepts, adaptation and resilience. And resilience is appearing more frequently. And the resilience of what is really could be referring to the energy system, such as the bulk electricity grid. Is that a resilient system to shocks? It could be referring to people or communities or cities. And resilience to what? It could be to resilience to climate emergencies such as extreme heat, floods, wildfires, power outages, and there can be coincident climate-induced hazards or emergencies as well as risks. And resilience is important to ensure health and safety of residents, productivity of residents and people, and good educational outcomes and good social outcomes. And for sure, there's a need for greater resilience to extreme climate events. So for example, there's extreme increases in extreme heat pretty much everywhere. And we see or have seen severe to catastrophic climate-related events from the past 2 years, unfortunately. So in 2021, in North America, hundreds are believed to have died during the Pacific Northwest heat wave. A lot of areas which did not have access to air conditioning because it's a very mild climate in general. And in the winter of 2020. Oh, can you mute, please?
Yeah, go ahead, Dr. Wei.
Thank you, sorry. And in 2021, there was very extremely cold weather in Texas, and the Texas power grid failed for several days. So there was a lack of power, and that was very dangerous for many residents when it was very cold outside. And this year, millions in Bangladesh were impacted by some of the worst floodings ever seen. And in China, there were heat waves which led to factory shutdowns and disrupted access to water for hundreds of thousands and rolling blackouts in some cities. And in Europe, there was, again, very scorching heat, which put strains on the energy supply and reduced hydropower and impacted nuclear reactors in France and so on. So many impacts. Here, I just want to comment on the scale of resilience and to just highlight that it can occur at different scales across these vectors. So geographically, it can be at the very local, at the level of the home, to the community, city, and regional levels. And then in terms of infrastructure, it can refer to end-use equipment at the, at the very local level, like backup power generation or distributed generation, such as solar photovoltaics and battery storage, and to very centralized energy systems or larger energy systems, such as the electricity power grid or the natural gas supply system. And there are, of course, past risks, which are probably not sufficient to look at in terms of historical risk, as well as current risks, near-term and longer-term risks, and that all those seem to be accelerating, unfortunately. And then the types of risk, and here I just wanted to highlight that there are acute emergency risks, such as a flood, a hurricane, extreme heat wave, and coincident events. But increasingly, one can think about resilience to everyday climate changes or everyday impacts from the weather, such as very hot weather every day during the summer, for example, in hot regions or very hot and humid regions. So we do need to think about chronic risks as well as acute risks when we talk about resilience. And again, the types of resilience can refer to individual, to community, to technology and infrastructure resilience. But again, I just wanted to highlight that social factors can be very important in terms of social connectivity, social communication, social trust during an emergency for communication and coordination. So some key fairness or justice principles for climate equity include restorative justice, recognition justice, procedural justice, and distributional justice. And the first, restorative, refers to the repair of harms done to communities in the past. Recognition justice is really hearing and recognizing different voices. So different people have different and valid perspectives. And procedural justice is similar in providing underserved and overburdened communities with a voice and a stake in decision making. So this is really looking at more bottom-up processes rather than top-down processes. And distributional justice, as its name suggests, just refers to the more equitable distribution of environmental, energy, and climate benefits. And this is from a recent paper by a colleague here at Berkeley Lab. And some energy equity objectives are shown here. And here I just wanted to highlight that equity and resilience can be pretty closely related. And so the three objectives here from the Energy Commission in California include advancing or improving access to clean energy, including products and financing, increasing clean energy investment in low-income and disadvantaged communities, including research, demonstrations, and emergency preparedness, speaking to greater resilience, as well as outreach and education in the communities. Finally, to improve local energy-related resilience, including resilience to grid outages and energy reliability, energy affordable, and ensuring health and safety. So I think the last slide here in this section for introduction is landscape mapping. And I just wanted to highlight that the focus today is shown here on the left, emerging imperatives in the center, and future imperatives toward the right for societal imperatives, demand and supplies, or energy demand and energy supplies. So today, the focus is on decarbonization and cost effectiveness. And increasingly, we need to keep in mind and ensure resilience to climate risks and equity of outcomes and burdens and benefits. And in the future, just to note that these may not always necessarily be cost effective. And on the demand side, of course, energy efficiency has been a major focus for the past several decades. And then we're increasingly seeing the importance of demand flexibility, so load shifting, peak shaving. We do a lot of work at the lab in demand response for electricity, but also pushing more towards conservation or using less or doing more with less, to sufficiency, which refers to deep conservation within planetary boundaries. And this is probably more for developed countries like the United States and OECD in particular. I won't talk so much about supplies, energy supplies, but just to highlight here that there's the emerging imperative for resilient, equitable decarbonization, or RED. And I just wanted to mention it in passing here, the connection with sufficiency, and that sufficiency or deep conservation can provide greater equity through more equitable distribution. So we can have limits on wealth accumulation and better distribution of wealth, for example. And that sufficiency can also provide greater resilience, because if we're using less energy or using less materials, then it should be easier to provision services, because we're not as stretched, it's not as thinly stretched. Okay, so just very briefly, the scope of the rest of the talk will focus on the United States and the Central Valley of California, for example. And equity and resilience are fairly local and regional issues, so that's just a note. And the resilience and equity here is focused on heat resilience, but of course there are a lot of interactions with heat, as we see in China and France. So there's drought, there's wildfires, or there can be wildfires, there can be air quality issues, there can be power shortages or power outages or rolling blackouts and so on. And here again, we're focusing more on emergency situations, which are worst case historical heat waves, but it's very important to consider chronic impacts of heat as well. So I'll just go to the CalTHRS project as an example of resilience and equity work. So this stands for a California Toolkit for Heat Resilience in Underserved Environments. And I just show some of my colleagues, including Tianjun Hong, whom some of you may know from the Building Urban Sciences division at LBL, and some of our partners here on the right. So this is just a background and objective slide. So extreme heat is now causes more deaths than other climate risks in most years. And it is also the most costly climate change impact in California by the end of the century. And this is primarily due to excess mortalities that are projected out to the mid-century. And some of the research objectives include developing methods to model heat resilience at neighborhood scale, and to quantify the resilience benefits of passive and active cooling measures during extreme heat in a disadvantaged community. And I'll discuss those metrics, and those include health and comfort metrics indoors. And finally, to develop a set of toolkit items to help disadvantaged community residents better cope with extreme heat, focusing on Fresno and the Central Valley. So I just wanted to flash very quickly some existing California state policies, just to show that it has some aggressive climate policies, as you probably know, including a 40% greenhouse gas reduction target in 2030 relative to 1990 levels, and a carbon neutrality policy goal by 2045, economy-wide carbon neutrality. And that there's a law that requires that at least 25% of cap and trade proceeds go to projects that provide a benefit to disadvantaged communities, and at least 10% go to projects located within communities directly. And that one of the key policy goals is 100% zero emissions vehicle car sales by 2035. And that one may actually be a law now, not just a policy goal. And there are a lot more that I won't cover, but just this is a snapshot. And as I mentioned, there are multiple challenges in Fresno and the Central Valley of California. Fresno is the largest city in the Central Valley, in the center of the Central Valley. And again, much of this city is highly disadvantaged and underserved, as it is across the whole region. Residents have the worst air quality. This is a closed air basin, so a lot of the pollution from the freeways, from the dairy farms, and from the oil industry activity in the south, all the air, the bad air, or the polluted air congregates in this valley. Residents have very high utility bills. It's very hot in the summer, and residents will experience more extreme heat days that will likely triple in 10 years. And there's a very low ownership and access to clean technologies such as electric vehicles and rooftop solar PV. And in California, as in other places, we have seen increasing income inequality for the last 20 years, at least to 2018, which is my latest data point. So there's increasing heat from climate change, and this is pretty universal, I think, but I just wanted to highlight that inland areas in California will have a 4 to 5 times increase in extreme heat from the current level here in blue to 2040, and this is 27 in gray. And that extreme heat is defined, is place specific, so it refers to a threshold of temperature which is above the 98th percentile of a given location. So the extreme heat in Fresno is 41 degrees Celsius, but in Oakland it's much lower temperature because it's much milder there. But if one were to look at a different threshold of not the 98th percentile, but something like the 92nd percentile or something, the 38 degrees, which is 100 degrees Fahrenheit, there are twice as many, there's much higher frequency, and there's a 2x increase in projected days above 38 degrees Celsius. But I just wanted to note that in 2021, already the number of days above 38 degrees Celsius exceeded this level projected for 2040. So again, we're seeing an acceleration of extreme heat. And of course, extreme heat has equity implications for indoor comfort and transportation. So some people may not be able to afford an air conditioner, or may not be afford the air conditioning bill in the summer, which can be very high. And heat wave impacts, there are many impacts. It's the leading cause of weather-related deaths. There's a greater risk for people who do not have access to air conditioning or can't afford to pay for their bills. There are very many vulnerable populations, such as the elderly and the socially isolated, who don't really have ties to the rest of the community, and those with underlying health conditions, including heart conditions, asthma. The very young and the unhoused can be especially vulnerable. And there are definitely heat-related disparities by race and ethnicity. So for example, there's a 56% higher death rate in heat for Blacks than whites in California. And by the way, this area is largely, well, there are a lot of Spanish-speaking residents in this area. So the approach is to develop a heat resilience toolkit that incorporates both community inputs and science. And so community engagement is important. So this is the kind of the recognition justice component that we talked about earlier, of really valuing perspectives and opinions from the community. And so one example of that is we really wanted to understand better how well community cooling centers work. And these are public facilities which are air conditioned and cool and made available to the public. Like they could be a public library or public recreational center, which is available to the community as a refuge from extreme heat if they don't have cooling in their homes. And we coupled that community engagement with a neighborhood scale building modeling that I'll describe in a moment, as well as outdoor measure modeling, which I won't discuss too much here in this talk. But components of the heat resilience toolkit include several components: community cooling guide, fact sheets, a heat vulnerability index tool, and policy and program recommendations, among other components. And I'll just flash some of those components to share what those look like. So what is community research or community science? Is really, research which is focused on the betterment of the community, and it's working together with the community. So it's trying to learn from the community, and it's hopefully long-term and connected. So we are planning to do follow-up work in Fresno, or we'd like to do follow-up pilot or demonstration work in Fresno. And the dissemination means are non-traditional, so not just conferences and journal papers, but it could be social media or community meetings for dissemination. And these are important for many reasons: community engagement and feedback to help researchers to understand how residents cope with extreme heat, and to better understand residents' needs and their preferences and their barriers to propose cooling strategies. The example here is how people view community cooling centers and whether they use them or they don't use them, or, and also to inform our modeling assumptions, particularly for the types of cooling equipment and the building stock that people are housed in. And we use a variety of outreach methods, including community meetings, focus groups, in-home interviews, and phone interviews. Focus groups were meetings of about 25 people, which were focused on a certain demographics, such as mothers or Spanish speakers or the elderly. And we worked in 4 disadvantaged neighborhoods in Fresno, primarily South Fresno. And we found, many older single-family homes in blue here in 2 neighborhoods. And this is just a Pareto of the year of construction. So the median was 1976 and I think 1942. So generally older building stock, which may not be so well insulated. And we utilize the neighborhood scale building modeling tool, CityBES, which was developed by Dr. Tianjun Hong here at Lawrence Berkeley Lab. And CityBES is an open tool for neighborhood to urban scale building modeling. And the team developed a residential building data set for several neighborhoods in South Fresno. And CityBES can model energy savings at the scale of 1 building or for a group of buildings. And it's publicly available, as I noted. And the overall workflow here was at 2 scales of modeling: at the prototype building single family model or multifamily model. And we also looked at district scale. So we looked at all of the residential buildings in a given neighborhood, which were, generally about 1,000 buildings or so. And this just shows the workflow to where we created baseline models of the prototypes or the neighborhood, and we created the models of the energy conservation measures or ECMs, and I'll describe those in a moment. And we ran simulations during a worst case heat wave with and without grid power available for passive measures. And then we can calculate resilience metrics, which I'll describe which metrics were considered to summarize results and analysis. And we did that again at the individual building prototype level and also at the neighborhood scale level, which is the district scale analysis. And we modeled 9 passive indoor cooling measures in a worst case heat wave with and without grid power available. So we considered several window treatments, including window blinds and solar control window films, which are thin films that can help reduce the amount of solar heat gain through the window, as well as cool surfaces, cool roofs, or more reflective, roofs like lighter colored roofs, and cool walls, more reflective walls, roof and attic insulation, radiant barrier, and natural ventilation. And then we also modeled 8 active indoor cooling measures and 2 passive outdoor cooling measures, including several different types of fans, several different types of air conditioners, including mini split ACs and room-sized air conditioners. So again, we modeled a worst case heat wave. So this was a study looking at an emergency event. We didn't really consider the chronic impacts of all of those days above 38 degrees Celsius. But here there's a worst case heat wave of 7 days. This was in 2006, I think, between 7 days between 42 and 44 degrees Celsius, or about 110 degrees Fahrenheit, with the grid power on and the grid power off. And so if the grid power is off, you can see that depending on the building vintage and insulation assumptions, that very dangerously hot temperatures can be achieved indoors without any cooling. We looked at a variety of resilience metrics during this worst case heat wave, including unmet degree hours, heat index, set, unmet degree hours, and predicted mean vote exceedance hours. And for each of these metrics, the metrics consider a variety of parameters. Some are just air temperature, some include relative humidity and air temperature, and some are more comprehensive, including temperature, humidity, mean radiant temperature, air velocity, metabolic rate, and so on. And each of them have their limitations. So clearly, if you neglect relative humidity, it's not quite complete, and so on. But it's important to note that there are thresholds, and again, these thresholds are not necessarily universal thresholds, but they're thresholds for cooling set point. So what's the temperature that you want to achieve, and thresholds for caution, extreme heat index caution, extreme caution danger, and extreme danger for heat index. And similarly, parameters or thresholds for grid on for set and grid off for set for at 28 degrees C and 30 degrees C. And for PMV, thresholds for thermal comfort and the unbearable limit. Just one simple example of a heat resilience metric is unmet degree hours. So if your temperature set point is 25 degrees Celsius, then unmet degree hours is defined as the total area under the curve for an indoor temperature versus time plot that is above a threshold temperature here. And the colored area is just showing that integrated area. So we found several key vulnerabilities for residents in disadvantaged communities in South Fresno. So firstly, a large fraction are uncomfortably hot at home during their during the summer. And we found about 15% lack air conditioning, and they're especially vulnerable. There are a lot of older air conditioners. In general, air conditioning costs were very high. A reasonable fraction were willing to plant trees or to open doors or windows in the summer, and a smaller number have solar control window films. We found also that most people prefer to stay at home during heat waves rather than go out to another cooled environment, such as a community cooling center, for a variety of reasons. And so most residents just prefer the convenience of staying at home, even if it's uncomfortable inside. And some people voice concerns about other people who are in community cooling centers, such as seniors reported being annoyed at young kids, and there was some concern with unhoused or homeless attendees. So this was important because the state may be investing a lot of funds in these cooling centers. And so it is very important to understand the limitations and the barriers that people face, and how to improve these types of community centers. In terms of passive measures, we found that solar control window films, roof and ceiling insulation, and cool walls were among the most effective measures, the passive measures overall, but natural ventilation is helpful in the top floors. But again, natural ventilation is a concern for some residents due to security concerns. And also, it's not appropriate to open your doors or windows when air quality outside is especially bad. And we talked about that earlier, that the air quality is very poor in general in Fresno. And then for active measures, fans improve comfort and can greatly reduce electricity bills. So this is just showing a reduction in electricity bills. So fans save on overall electricity use by allowing a higher air conditioner thermostat setting. And we found that they are an opportunity for greater awareness and education. And then secondly, we found that homes with swamp coolers or evaporative coolers only, so homes which don't have an air conditioner, can really benefit from getting an air conditioner, not surprisingly. So this is just the improvement or the reduction in this metric of set unmet degree hours. It's nearly 100% reduction. So getting air conditioning definitely helps. And our heat vulnerability index tool maps exposure, sensitivity, and adaptation by census block or pretty small neighborhood region. And that rolls into a heat vulnerability index. So just showing that the highest vulnerability in Fresno is in the south and central area with high sensitivity and low adaptation. And one note here is that we take into account the building condition. So we call that the building heat resistance indicator. So we're taking into account, or trying to take into account, the vintage of residential buildings, as well as the types or the distributions of the types of cooling systems, like do they have a swamp cooler, an air conditioner, and is the building insulated or not. And our toolkit elements target various stakeholders that vary from the local community to state level agencies. So this is the community-based organization to state level agencies. And this is our toolkit element. So we're targeting policymakers as well as local and national government, non-government organizations. This is just an example of some of our fact sheets for cool walls and for air conditioning systems. So we're just giving some background on what the measure is, how it can benefit, how you can install it, and some basic cost considerations. And so as an output, we derived a lot of policy and program recommendations from the CalTIRES project. And I won't read all of these, but this is just a subset of them. So for an example, consider strengthening the requirements for cool walls and cool surfaces. So when you are repainting a home or re-roofing your roof, it's a great opportunity to require more cool walls or cool surfaces. And second, that California's and building standards in general, building codes and standards should be updated or upgraded to promote extreme heat solutions based on human outcomes. So that is to say, minimizing added mortality, illness, and misery. And we need mechanisms and programs to ensure adequate cooling in existing homes, especially in disadvantaged communities with older buildings. So for example, current building codes and standards, which are for new construction only, have minimum heating requirements, but they do not have minimum design standards for cooling. And I'm just going to skip down to this one. So all homes without an air conditioner should get at least one air conditioner heat pump to safely withstand extreme heat waves. And then for community cooling centers to be more attractive, they need to extend or enhance the services, hours, or activities, and they could also be expanded into emergency response centers to provide more multifunctions, or these are known as community resilience hubs for a variety of hazards. Okay, I'll maybe just skip this, except to say that community science and community partnership is important to improve R&D effectiveness and supporting greater equity, and that we're actively disseminating this project with the community as well as with policymakers, and we're starting a related project to improve heat resilience in milder coastal climates. So these are areas that are not accustomed to having extreme heat, but are still increasingly at risk for extreme heat waves, and they generally lack air conditioning. Okay, so just a few slides and then I'll wrap up for next steps in future work in policy and RD&D. So the key one here is what is the value of resilience that can better justify resilience investments, such as undergrounding the grid or some of the passive cooling measures that I mentioned, or could be perhaps the resilience value of solar and storage. So here we really need to develop non-energy metrics and quantify their impacts to support codes and standards development to include resilience in addition to energy efficiency, for example. And to guide future investments in extreme heat resilience, mitigation programs should dedicate resources to monitoring outcomes. So there's a lot of investments that are planned in the near term in California and also across the country, really, with the Infrastructure Act and the Inflation Reduction Act earlier this year. And how to model regional to national decarbonization with resilience and equity as key objectives or key themes is a challenge because it's kind of very broad. And also, in particular, if equity is understood to be a more local phenomenon where it's important to get community inputs and to allow the community to have a seat at the table, to be stakeholders in the process of developing regulations or rules, then it can be a question of, well, what's the right scale of that? Is that at the scale of a village or a town, a city, a county, because there are so many people and so many different communities, and they may have different priorities or different, they may face different barriers and so on. But just to speak to this key gap of quantifying the value of resilience. So And I think this is my last slide, but yes, it is. So typically energy investments such as energy efficiency are made on the basis of energy and greenhouse gas savings, and there could be some cost benefit or NPV, net present value calculation. They're not typically based on resilience values or the value of resilience provided to emergencies or even chronic everyday climate changes like extreme heat, increasingly extreme heat, or human impacts, including deaths, illness, and misery, which we call DIM. So this is just a schematic or a cartoon showing the NPV versus the reference case of a prospective investment where it can be, the NPV can be below zero. And this is just to show that there can be a range of sensitivity. So what this is the median value, can be below zero or not favorable without the value of resilience. And so investments for resilience may not be cost effective or the cost benefit ratio may not be favorable. But with an appropriate valuation of resilience in terms of human impacts, health and safety, productivity, and so on, this can shift the NPV into positive territory with the valuation of resilience investments. So the challenge really becomes how do we value things beyond just energy and greenhouse gas reductions, and how do we measure that and how do we monetize that? So with that, I'll just conclude and thank you very much for your attention and again the opportunity to present. The website here is cal-thrives.lbl.gov. This is my email, mwei@lbl.gov. If you have any questions, feel free to email me. So we have some additional publications here just for reference, but I'll just maybe stop here and just open it up to any questions.
Right. Thank you very much, Dr. Wei, for the very interesting presentation. Okay. So let's see if there's any questions from the audience. Okay, if not, Dr. Wei, I have a question. It's not like a question, rather like I just want to know if you have any comments on this. Okay, so I'm also working on resilience. My research is focusing on urban resilience, dealing with all sorts of natural hazards, natural disasters. Currently, we're working on the urban floods. So for the past few years, when we deal with resilience, the topic of resilience, we notice that there's usually really like tricky question we have to bear in mind throughout the whole process. That is the conflict of interests among different systems. Like for example, if we're talking about increasing the resilience of transportation system, like increasing connectivity, so we have to build more roads. But in the meantime, it actually can create a lot of segmentation for wildlife habitats. So you're actually decreasing the resilience of ecological systems by building more roads. So it's like a really obvious conflict of interest between different systems. So I would just want to ask you, do you have that sort of similar comments or similar observations when you work on the heat resilience?
I'm just taking some notes. Yeah, that's a really great question. Thank you so much, Dr. Tang. I mean, yes and no, I would say. So I think that that's a really excellent point, but it is a challenging point because you have to balance a lot of interests. In your case, which covers, it could cover, a large area. If you're talking about flooding, it could be a large region instead of like a city in my case. And for sure, there can be conflicts of interest. I can just give you a few maybe simple examples here from what I've seen. So for, resilience to power outages, which we've seen, in California, as you may know, due to wildfire risk, people have, the utilities have shut down the power grid so that there's not such a high risk for extreme wildfires. So in those cases, the question is, well, what should people do for backup power? And so a lot of people are saying, well, we should get backup generation, or the utilities may have backup generation. But obviously, if you have a lot of diesel backup generators, then it can be a problem because the air quality can just be worsened. So it can make air quality, but also, diesel generator, if somebody has a lot of fuel, I mean, it might just actually cause an accident, so there's some concerns. I have a friend who's seen that, and he was just concerned about that. But also, energy efficiency and resilience, they may be, if you're talking about insulating your home, your walls, your attic or roof insulation, that's consistent with being more resilient to heat. But on the other hand, if you go really far and you say, well, you really want to improve and seal up the home so it's very well tightly insulated, then that may not be so great, because then there's not really adequate ventilation and air exchange during a heat wave, or if there's a power outage. So there can be some tensions or some conflicts. But I haven't really thought through as I mentioned in my scope slide, all of the interactions, and that is something that we're interested in modeling some of the coincident risks. But I think you're talking about something different, which is more of the impacts of some major intervention, which may be helpful for one risk, but it could be damaging for another ecosystem or for another group, perhaps. And I would just say that this balancing of interests is very difficult here, because a lot of people, I'll just give you a very real world example. I believe in China, there's a lot of high-speed rail. There's a lot of high-speed rail in France and in Europe and in Taiwan and, a lot of countries. California has a high-speed rail project for about 20 years, or maybe, there's I think a funding bill maybe 15 years ago, but it's been very difficult to construct. And they're starting to construct it in the Central Valley of California, which is the subject of my talk, which isn't the original intention. The original intention was to go from Los Angeles to San Francisco. So there are a lot of competing interests. Some people do not like that, and there could be lawsuits. Or similarly, desalinization, it just takes a very long time because of competing concerns or environmentalists or legal reviews or lawsuits. So there's definitely a lot of conflicts which lead to delays, and that might be one of the problems that you're describing, that if there's a conflict, there could be some just delays in moving forward. So anyways, that's a long response, but that's a great point. But no, I think I haven't really done a huge amount of work, and I think that requires more, another level of modeling sophistication also.
Yeah, definitely.
So I'd be curious in learning more about your work and how you take that into account and balance it. And,
no.
Yeah, it's difficult, very difficult.
Yes, indeed, it is very difficult. But I think the point you raised in the beginning slides, so you mentioned that we have to clarify resilience of what and resilience to whom first before we can talk about this concept. I think that's a really good point. And in urban resilience, people always saying that, as you said, there's a lot of trade-off we have to make. So for research purpose, I think it would be better if we clearly draw the boundary first and narrow down our scope, and then we say how are we going to build resilience for something and of something, right? So I think that would be some promising way to do it. Another point is
sorry, Dr. Tang, can I just make can I just make a comment on that?
Yeah, go ahead.
Sorry to interrupt you. I agree with you that it's important, and I think one analogy there is when we do life cycle cost analysis. There's sort of a scope is the first figure, like what is the scope and what's included upstream, downstream. I do think that's important because otherwise it gets kind of particularly sometimes ambiguous or unclear sometimes, like what are we trying to do and what's the purpose.
Yeah.
So I think that it is important, and so I'd like to see that maybe just a little bit more formality in the scope, just as you said, just as you suggested. So I'm just in agreement with that.
Cool. Yeah, definitely. Just when you talk about the for different residents, it's just a reason. Another interesting point to me is that for social studies, we sometimes might even forget, but it is a really not unusual to see that there's disparities among different groups of people. So do you think for our heat residents, there's also like disparities for different economic, socio-economic groups? Like, for example, if I relate that to myself, even with the AC in the house, I always had a fight with my wife about when to turn it on and when to turn it off. Like, because sometimes I think it's still hot, but she said, it's cool enough. Let's turn it off. But I was sweating, but she was like, I'm already feel chilled. Like there's a huge disparity between different socioeconomic groups. So how do we, like, from your perspective, how do we, probe the mechanism that perpetuates all these disparities or inequalities, and how are we going to do about that?
Yeah, it's a great question, and your question makes me smile because I have the different same experience at the different polarity, which is the heating system. Because I'm a green guy and I don't like to burn natural gas, I like to not use my furnace in my home. And it's not that cold, but it does get, below. I mean, it's a heating season some days. So I'm always turning down the heat, whereas my wife wants to have heat. And so there's a tension there and a conflict similar to your conflicts with air conditioning. And so what you're highlighting is that the scale, again, of the disparity, it could be really, really hyper local, like at the individual, at the family level, or it could be in the office building, or it could be in the movie theater, it could be in the hospital, and you see things about overheating or probably more overcooling, sometimes, and that women and men may have different set points, but it could definitely vary among men, or it could vary among women. So I haven't really done a lot of thought or thinking or research along those lines, but it's a very interesting question, and it's potentially an area for very interesting research. I mean, one interesting research area, which I'm sure you're familiar with and people are familiar with, is more personalized heating and cooling systems. So today we tend to heat the space, and we don't, it's kind of wasteful in a sense if you're heating a large space and there's only one person in it, in a hotel or in a hospital or office building. Like today, we know that like my lab, or maybe at your university, but the occupancy is not very high, but buildings are not very intelligent. So I was considering putting in a slide or some statement in my talk about future research for personalized cooling systems, which is really to say more intelligence in the cooling. Like in America, I mean, we might have larger homes. So you can imagine a really large home, like 200 square meters or something. I'm not sure if that's the right conversion, but you might cool or heat the entire home, but that's kind of wasteful. So just the prospect of more intelligence or more personalized. I mean, at the opposite extreme, it would be like a personalized fan or personalized. We don't really have a personalized air conditioner. Maybe we can develop one with storage to be very hyper resilient, low power and low cost, but we do have low cost, low power fans, which provide individualized, personalized cooling. We can have individualized, personalized heating for your chair. You can have individualized heating maybe for your jacket, or maybe, blanket when you're sleeping, with your spouse or something. So there could be some technology mechanisms or sensors which are more intelligent and provide greater efficiency, lower, it's an area just for development, and some of those exist, some of them do not. It's something I'm quite interested in. But in terms of the social factor, like what is driving this, or how do you model this, or I don't really know. I mean, I think it's a really great question though, because everybody's different, and some of these metrics that I shared, like SET and PMV, they're all subjective. It's all subjective, and it's just like the bulk of people feel comfortable or uncomfortable, but there'll always be some distribution, and it won't be comfortable. And so, you try to maximize the comfort, but how do you really achieve that? It's difficult. So yeah, it's a good question, but I can't really answer too much on the social mechanisms or probing side, but it's good food for thought.
Yeah, I agree with you, fully agree, because a similar situation can be found in Singapore. It's very usual during the daytime in a cinema. There's only 1 or 2 audience in a cinema hall, but there's a really strong AC, working all day long. And I think I fully agree with you. That's totally a waste. And yeah, there's a lot of things we can do on that. Yeah, and also the smart technology use, monitoring the space and interior building space. Yeah, because when I was doing my postdoc project back in Cambridge, there's another team. We work really close, and they actually trying to build a digital twin for a single building and achieve the 100% monitor of the operations of the building. I think that's one promising future way we can go, right? I fully agree with you on this point, and that's also we see that point in disaster risk reduction as well. The disparities among social groups, that's a really big topic.
Yeah,
okay.
Yeah, definitely. There's work in material science also, like smarter materials which are more reflective in the summer, but less reflective in the winter, because you don't want to reflect the sun in the winter so much. Or it could be smarter clothing that does a better job of providing comfort or cooling. So yeah, there's a wide range of things there, but definitely I think kind of the censoring has a role also, which we don't necessarily do too much of.
Yeah, definitely. Those sensors, we can see that as enabling tools, and also some people just say we can put a bunch of ICT technologies into the work, and it will work. But sometimes people just forgot that it's a city, it's a complex system, not just like a sand pile that you just keep adding things on it. So yeah, there's a lot of interesting topic we can debate about, or people can discuss it about. But anyway, I think
definitely. I think the response to some of these things also is interesting. The social factors involved in deploying some things which are maybe more just collect to the trend in the direction of collecting more personal data is interesting, because some people may not care. I probably wouldn't care, but some people may feel, oh, that's they want my body temperature now. Those things might not be so. There could be a large range in responses and some hostility, but some people don't really care. So that's interesting also, and that's just interesting that research could be done there too.
Yeah, definitely. The data is another headache. Yeah. Okay. Thank you very much, Dr. Wei. I think we approaching the end, and thank you very much again for your very interesting presentation and very enlightening. And thank you for sharing with us today. And I hope if the audience have any more questions, you can contact Dr. Wei via the email and other website. And I think this is it today. So let's call it today. Dr. Wei, nice to meet you.
Thank you very much, Dr. Tang, and thank you everyone for participating and listening to the talk today. And I will just leave some information in the chat just for reference in case people missed it. So thank you again. Yeah, all the best.
Thank you.
Yeah.
You too.